Hello, in this video we will cover section 2.3 Business Applications using Quadratics. The objectives of the section are pretty much the same as what we covered in section 1.6, but this time we're going to be looking at quadratic applications of these ideas instead of linear applications. But we're still finding break-even points, we're still thinking about market equilibrium. Because we are looking at quadratics, we'll have an opportunity to minimize and maximize functions. So we begin with a little bit of background about monopoly markets. This is just one area where quadratic functions might occur naturally. We've already seen that if you want to compute revenue, that's going to be equal to price times a number of units sold. So in this instance, I'm just going to call price P, and number of units sold will be X. In the previous section, the price was just a constant, so maybe your price was $30 per unit. But in this section, we're going to allow the price to be a function. Now, specifically, if you were looking at a monopoly market, it might make sense that the price was actually the demand function. But generically, we're going to say that P is equal to f of x. So if we substitute that idea into this equation up here, what we get is that your revenue would be equal to P times x, which would be then your function times x. So if we wanted to just think about a simple example, let's suppose that your price is always going to be $300 maybe dollars minus x units, where x is the number of units sold. Then the revenue function would be the following. Your revenue would be px, but since p is actually 300 minus x, we substitute it in, we multiply by x. Then when we would distribute the x into parentheses here, sometimes I'll even show this just on paper. So x would get distributed in. That's how we would get this function here. And we notice that it's a quadratic function. It has that x squared term in it. So the point of that example is just to say that quadratic functions can exist in the natural world. Monopoly markets are just one situation where that might happen. If we are given quadratic functions, then we might be interested in finding the break-even point of the situation that we're looking at. So if you recall from the previous section, break-even points can be computed if you set the cost equal to revenue. The other way we talked about last time, I'll write this down here, and we can reference this later if we want. If you had generated a profit function, then break-even points can be found by setting that profit function equal to 0. But of course that would require us to have a profit function. Let's look at the first example here at the bottom of the page. Suppose we're in a monopoly market situation. We are given a total cost per day of producing a high-tech product. It's given by this C function that's listed. Suppose further that the daily demand for the product is given by this price function. So price is equal to something that's based off of x, which is our quantity. Then we want to find the number of units that would give the break-even point. So as soon as the question asks for a break-even point, what you should immediately be thinking is what's listed right up here above. In order to get a break-even point, we would want to set cost equal to revenue. So I know I'm going to get my break-even point if cost equals revenue. Then we want to list what our cost and our revenue functions are. Now the cost function is just given to us. So there's no particular need to rewrite this, but some people will prefer to see the terms in descending order. So I'm going to rewrite this so that I have 2x squared in the front, and then I'll have my constant at the end. Now, once I've listed my cost function, which was given, I need to come up with a revenue function. Here we're not given a revenue function, we are instead given a demand function, and it's in terms of P being the price. Up there at the top of the screen, you'll see how we were thinking about that. So revenue is always going to be equal to a price times x, and then that's how we're going to generate our revenue function. So I'll copy down that format. It's going to be equal to p times x, but in this example, we know that our price is actually this, so we'll substitute that in for p. This is 500 minus 2x. And then that's going to be multiplied by x. Like we did before, if we would like, we can distribute that x into parentheses. When we do so, we would find out that our revenue is in fact equal to 500x minus 2x squared. Now, if you like, you can rewrite these in descending order so that r is equal to negative 2x squared plus 500x. It's not strictly necessary, but if it makes you feel more comfortable working with these two quadratics, then that's a good step to take. All right, what was our goal? Our goal was to find a break-even point. We wanted to set cost equal to revenue. We now have a cost function. We now have a revenue function. Let's go ahead and write that those are equal to each other. In order to solve this, we're going to want to get one side of the equation equal to 0, so I'm going to need to somehow move these pieces over. The algebraic step we take is that we are just going to add on the opposite, so I'm going to add on 2x squared to both sides of the equation. That's going to get rid of this piece. If I add on the opposite of 500x, that's the same as subtracting 500x. So then in our next line, we have 0 on the right side of the equation, and on the left side, we get 4x squared minus 400x plus 3600. Now, when you're looking at this line, we have a quadratic is equal to 0. In order to solve this, you have two options. I'll write down what they are off to the side. You can choose to factor at this point, or you can choose to use the quadratic formula. I'm going to choose to factor, but you are welcome to use the quadratic formula. In either case, if you can simplify this function a little bit before you begin that process, it's going to make both of these options easier. So when I say simplify, there's two ways you can think about that. This is an equation, so you're allowed to divide every term in an equation by the same number. We'll notice that all of these numbers are divisible by 4, so that's going to be a strategy that helps us simplify this. Alternatively, you could think about factoring out a common factor of 4 on the left side of the equation. I'm just going to show it, though, by dividing everything by 4 in this equation. It's not necessary, but it does make the next part a little bit nicer. In order to factor this, you need to come up with two numbers now that are going to multiply to be this constant here at the end, and that will add to be this middle number. I don't have a lot of room on this screen, so what I'm going to do is I'm going to just go up over here in the margin, and I'm going to list what my objective is. I need to multiply to positive 900. So I'm just going to list every pair of numbers I know that would do that. Let's see, they are 1 times 900. I could check, do these two things add to be 100? And the answer is not yet. Then what other numbers multiply to 900? I would have 2 times 450, 3 times 300, 4 times 225. At some point, I stop being able to do this in my head, and I'll just pull out a calculator, so I could take 900 divided by 5 to get the other number. And we see that it's 180. We can proceed in this manner. This would be 900 divided by 6 would give us 150. 900 is not divisible by 7. You get a decimal. It's not divisible by 8. You get a decimal. So then 9 times 100 would be 900. And you can check right now, we're getting really close. If you add these two numbers together, you don't get 100, you get 109. But we are really close to having the two numbers we want. We just need to go a little bit farther and say 10 times 90 would give us 900. These are the two numbers you want. Now, you want to be careful that you actually pick numbers that multiply correctly and add correctly. If we make both of these negative, they will multiply to be positive still. So that's this positive down here. But now that they're both negative, we can add them to get this middle piece here. So that's a bit of an algebra review, but if that was helpful, I hope it was. Our factorization here is x minus 10 and then x minus 90. All right, in order to solve this, we're going to rely on something called the zero product property. If two quantities multiply to get 0, then one of these two things has to be 0. So we can go off here to the left, set them equal to 0 independently. X minus 10 equals 0. x minus 90 equals 0. Solving these, we would find out that x equals 10 is a solution, and x equals 90 is a solution. When you're working in WebAssign, I believe that you will have to enter these as just a comma-separated list. So it might be nice to take a minute to reflect at the end of this example. In the previous section, our functions were linear, so we only had one break-even point, but here we have two different values where if you produce 10 units, your company breaks even. If you produce 90 units, your company breaks even. So the interpretation of this break-even point is fairly different than what we had last time, but let's go ahead and look at a graph of it. All right, so here's the graph, and what you're going to notice is that because we have two parabolas, one of them opening down and one of them opening up, we have two points of intersection. So if I was talking about this algebraically, I would say there's two points of intersection. However, if you're talking about this in terms of the context of the example, we would say there are two break-even points, and the company is going to be profitable anytime the revenue, which is this darker line, is above the cost, which is that lighter gray line. If you actually wanted to be able to determine what is the maximum revenue, you would have to, at this point in the semester, you would have to rely on some knowledge that you might have out of an algebra class. So let's review a little bit. How would you find the maximum, or minimum if that was the case, of a quadratic function? The key idea here is that anytime you are interested in finding a maximum or minimum, those will always occur on quadratics at the vertex. So that's just something to highlight, to remember. This strategy I'm about to describe is only going to be useful if you're trying to find maximums or minimums. So let's go through how we would do this. We have 4 steps, but the first 2 are things you do, and the last 2 are ones are just how to interpret your answer. So first of all, to find a vertex, you are going to use the vertex formula. So the vertex formula says that the x-coordinate of your vertex is equal to negative b over 2a, and we can use that to find the x-coordinate. Secondly, if you needed to have a y value, you can plug this x value you have just achieved back into the function, and that gives you the y value of the vertex. Then when you're interpreting your answer, the x value you have computed is always going to be a number of units that were needed. And then the y value you computed, that's the actual maximum or minimum, if that was the case, of the function. Now, this is a calculus class, and what we're looking at here is a really rudimentary way to compute minimums and maximums, but we haven't actually talked about any of the calculus of the semester yet. So once we get into our calculus ideas of being able to find a derivative, which is still going to be several weeks away, we will eventually have tools that are going to allow us to generalize this process. So this is specifically true in these examples, but we will have stronger, more powerful tools that will let us find minimums and maximums of other types of functions later on. So let's go ahead and find the number of units that maximize revenue in the previous example. I'm going to scroll the page down just a little bit so that I can reference the equations down here at the bottom of the screen. If you wanted to maximize revenue, I'm going to start by just writing down what the revenue function is. R is equal to, and I'm going to write this in that descending order that sometimes feels more comfortable than the notation that's shown here. I see the word maximum, so right here I'm going to maximize revenue, and so then I immediately know that I need to use the vertex formula. So we're thinking about a vertex. X is negative b over 2a. Now, it's fine if you don't list what a, b, and c are, but just for your reference, if you're feeling a little bit rusty about quadratics, a is always the number attached to the x squared, so in this example, negative 2. B is always the coefficient on x, so in this case it's 500. C is always the constant, so if you don't see a constant, the implication would be that it's 0. I'm not going to actually use C, but some of the formulas, like the quadratic formula, reference C, so it's just useful to remember what these are. Let's go ahead and plug them in. we get that x is equal to negative 500 over 2 times negative 2. So that's negative 500 over negative 4. And then when you divide that, you get 125. Now, it's useful to put a label on this number, and that is going to help us answer the question up here. The label that will be assigned to x in this example, and for most of the examples in this class, is just the label of units. So we find that if we produce 125 units, we have achieved the vertex, basically. So since a vertex corresponds to a maximum or a minimum, it would make sense that we need 125 units in order to maximize the revenue. So let's go ahead and box this in. Now, this is not the maximum revenue. In fact, the question does not ask us to find the maximum revenue. We just needed to find the number of units that will maximize the revenue. If you want to find what is the maximum revenue, we take units into the revenue function, and that gives us the revenue associated with this number. Instead, what this function asks is to find the cost associated with maximizing the revenue. So then we need to reference the other equation that's listed down there on the graph. We know that C is equal to 2x squared plus 100x plus 3600. And then what we would like to do is we would like to figure out what is C of 125, and that would just be what is the cost if we produce 125 units. So we plug the numbers in and pull out a calculator, punch that through, and you should get that the answer is 47,350, and we'll call that dollars. So something interesting has happened in this example. We set out trying to maximize our revenue, and when we look at the graph, we have a maximum revenue. Now, we didn't compute it, but if we had plugged this number into the revenue function, you would have found that the maximum revenue is $31,000. But our cost ends up being more than our revenue. So you could infer that the business is operating at a loss. We tried to maximize revenue, but our costs were so high that we actually lost money. We have a negative profit. So the implication here is that maximizing revenue is not going to guarantee that you're going to maximize profit. So how would you maximize profit? Well, remember the first thing we computed about this example was we found 2 break-even points. We know that the company is going to break even, so we'll have 0 profit if they produce 10 units or if they produce 90 units. So in order to have a maximum profit, you have to be somewhere between these 2 break-even points, so some number between 10 and 90. And right now, just looking, based on like a visual inspection of the graph, it's very difficult to see what that maximum profit would be. It's pretty clearly not going to be a number really close to the break-even point, because the difference between these 2 functions is really small, which would mean that your profit is really small. But somewhere in the middle here, whatever number maximizes the distance between the revenue function and the cost function, that's going to be the number of units that's going to maximize profit. But right now, what we're observing is that if you look at a graph of revenue and cost, it's hard to know what that value is that's going to maximize profit. So let's go ahead and start that computation of how would we maximize profit for this situation. What we are looking at here is these instructions at the top. We have a daily total cost function, which was the same as the previous examples. We have this revenue function, same thing as the previous examples. The instructions this time are we want to find the profit function. After we find the profit function, then we want to find the number of units that will maximize profit and then find the maximum profit. Let's go ahead and begin, though, by finding that profit function. If you recall, just from a previous section, you can compute profit by taking revenue minus cost. So in this example here, this is going to be equal to negative 2x squared plus 500x. That's our revenue. Then we're going to subtract off the cost. Make sure you use parentheses here. And then in parentheses, you have 2x squared plus 100x plus 3600. So you do want to make sure that when you subtract, this negative sign actually applies to everything that's inside. Some people will show this by turning it into a plus sign and then physically putting a negative sign on any of those. That's fine, but that's not strictly necessary. You could just like reference this negative sign every time you look at a number inside parentheses. So we have negative 2x squared minus 2x squared. That gives us a negative 4x squared. Then you have 500x minus 100, so that'll be plus 400x. And then you have minus 3600 at the end. And this is our profit function. Now, it's very tempting when you look at a function like this to maybe do something you're not technically supposed to do on the function. We have found the profit function. That was the first question that was asked, so we have correctly answered that. But as we read the next part of these instructions, it asks us to find the number of units that maximizes profit. It's a good idea to pause and read those instructions and then just remind yourself, okay, if I wanted to find a maximum profit, what do I need? I need a vertex, so I should next start computing the x value of that vertex. So let's write down vertex. We know that x would be equal to negative b over 2a. And the benefit of doing this is now we aren't going to accidentally try to factor this. Factoring it would give you useful information. We'll talk about that later, but it's not going to answer the question at hand. Okay, so we are finding the vertex. I'll go ahead and write down what a, b, and c are just for reference. For thoroughness on this example. A is the coefficient on the x squared, that's negative 4. B is the coefficient on x, so we have 400. C is the constant, this time negative 3600. So when we plug those numbers in, x is equal to negative 400 divided by 2 times negative 4. This is negative 400 divided by negative 8. Which is then going to be equal to a positive 50. It might be nice to put a label on this. We see that x is equal to 50, so this is going to be 50 units, so that we don't accidentally label it as dollars or something. Let me go back and reread what the question was asking me. It said, find the number of units that will maximize profit. I have a number of units on a vertex, so that's going to be the number of units that's going to maximize profit. After that, it asks me to then find the maximum profit. So the maximum profit is what you would get by plugging this back into the profit function. You could think about that as being the y value of your vertex, but in this case, that would just be equal to the whatever p is. So this is p of 50, and then we can go ahead and plug 50 into that equation. So negative 4 times 50 squared plus 400 times 50 minus 3600. And when you go ahead and plug that in your calculator, you should get 6,400. This time the label, this is P is what we were computing, so an appropriate label would be dollars. So we can kind of see this happening over here on the graph of the profit function. This is not something that would be given to you necessarily, but if you had it, or if you just wanted to see what is going on graphically, it would look like this. What happens is you have break-even points anytime your profit was equal to 0. So that's what we computed in that very first example, 10 and 90. If we produce 10 units, we break even. If we produce 90 units, we break even. We said that probably the maximum profit is going to happen somewhere between 10 and 90, and it actually happens to be the exact middle point, so whatever number was exactly halfway between 10 and 90. And then the height of this graph gets all the way up to 6,400 at the vertex, and that corresponds, of course, to the value of the function, so that's the maximum profit. So I know that we have figured out these two break-even points in a previous example when we had the cost and revenue functions and we set them equal to each other. But let's suppose you didn't have these two functions. If you only have the profit functions, how would you go about finding break-even points? Well, graphically, that happens anytime they're on the x-axis, so that would be like we would have to find the x-intercepts of this function. And if you recall, the way that you find x-intercepts on a quadratic equation is you just set it equal to 0, and then you can either use the quadratic formula or you could factor it. So let's go on to the next example. This one's going to be a little bit longer. So suppose a company has fixed costs of $2,400 and variable costs per unit of this many dollars. Here, X is going to be a total number of units produced. Suppose further that the selling price of the product is this, so we have a price function given to us. We want to do a couple of things, but we're going to start by finding the break-even points. Now, before I can even find a break-even point, I'm going to need to have a cost function and a revenue function. Remember that cost is equal to, it has a fixed component plus the variable cost times a number of units. So in this example, they tell us we have a fixed cost of $2,400. They tell us that the variable cost is 15/16 x plus 1,200, and then the number of units is just going to be x. So we'll distribute the x into parentheses, and then write these in descending order, and we'll have our function. So 2,400 plus 15/16 x squared plus 1,200x. C is equal to 15/16 x squared plus 1,200x plus 2,400. I'm boxing it in just for my reference, but it's not the answer to the question necessarily. Let's come up with our revenue function at the same time. Revenue is equal to a price times x, or times the number of units. So in this case, it's equal to 1,300 minus 1/16 x times x. So that's 1,300 x minus 1/16 x squared. So I'm going to write down that revenue is equal to negative 1/16 x squared plus 1,300x. Okay, now that we have the cost function and the revenue function, we can find a break-even point by setting them equal to each other. So I recommend that as you show your work for an example like this, you try to leave like little written comments that describe what you were doing. So I'm just going to write down like the phrase break even C equals R, so that whoever's reading this later understands what I was about to try to do. Okay, so let's do this. 15/16 x squared plus 1,200x plus 2,400 equals negative 1/16 x squared plus 1,300x. All right, it's an equation we want to solve. We want to get 0 on one side of the equation, everything else on the other. I'm going to choose to move these pieces to the left side of the equation. I'm going to add the opposite of this term. I will subtract 1,300x squared from both sides of my equation. Sorry, I don't know why I said squared, just 1,300x. So on the right side of my equation, I get 0 is equal to, on the left side, thankfully and blessedly, somebody prepared this example ahead of time, and we don't have to deal with fractions, at least not at this point. We get x squared minus 100x plus 2,400. You can solve this in any way that you like. You can factor, or you can use the quadratic formula. I'm going to choose to factor here. I need to find two numbers that multiply to be 2,400, and they need to add to be 100. So we go ahead and start making our list. I'm going to just start at 10 times 240. I see that these don't add up to 100, so I'm going to skip down a little bit. I'm going to see if I could divide it by 15. So let me check 2,400 divided by 15. is 160. That doesn't seem to work. I'm going to jump to 20. 2400 divided by 20 is equal to 120. Now this is a really tempting answer because if I make the 120 negative, they actually add up to be negative 100. The problem is if 120 is negative, they don't multiply to be a positive number, so it's tempting yet unproductive. Let me go ahead and jump to 30 next. And we know that 30 times 80 would be 2400. That still doesn't add up to 100, so we continue on. I'll go down to 40, and then 40 times 60 is going to work. So we see these two numbers, they add up to 100. Let me make them both negative. Now they add up to negative 100, and they still multiply to be that positive number. Okay, so then x minus 40, x minus 60 are the two numbers in question. To finish solving, we're going to find that x is equal to 40 or 60. So these are the two break-even points. Next, let's find the maximum revenue. We should go ahead and copy the formula for revenue from the other page. Once you have that, then we know that to maximize a quantity, we need to find the vertex. X is equal to negative b over 2 times a. So in this case, negative 1300 over 2 times negative 1/16. If you want to do this by hand, one way of doing it would be you could take half of 1300, so this would be negative, what is that, 650, and then you can multiply by the reciprocal. So we are right here, you have a number being divided by a fraction. This is division. So if you're dividing by a fraction, that's the same thing as multiplying by a reciprocal. So then this would be multiplied by negative 16 over 1. If you prefer to just plug it all in the calculator, that's also fine. Either way, we're going to get 10,400. Now, it's really tempting to put a dollar sign on this and say, hey, that's my maximum revenue, but in fact, it is not. To find the revenue, you need to put that number, 10,400, back into the revenue function. So this one, don't try to do any of it by hand, just put it in the calculator. Negative 1/16 times 10,400 squared plus 1,300 times 10,400, and then we see that this should be equal to $6,760,000. So definitely that's a lot of money. Let me go ahead and put the dollar symbol on this. But as we've seen previously, just because we have maximized revenue doesn't necessarily mean that we will have a maximum profit. So let's go ahead and form the profit function from the cost and revenue functions. To do this, we know that profit is equal to revenue minus cost. I'm going to go ahead and copy those from the previous page. All right, now we just need to combine some like terms. So we should have profit is equal to, if you take negative 1/16 and then subtract 15/16 more, you end up with negative 1, so just negative x squared. If you take 1,300 minus 1,200, you get 100. And then if we subtract 2,400, we end up with just negative 2,400. So that's our profit function. To find the maximum profit, we need to find the vertex of the profit function. So x equals negative b over 2a. This time b is 100, a is 1, sorry, negative 1. So we get negative 100 divided by negative 2 is 50. And if you think about the answer on the previous page about the break-even points, our break-even points were 40 and 60, and so then it would make sense that the maximum profit would be halfway between the two break-even points. I'm sorry, I said that wrong. This is not the profit, this is the number of units required to maximize profit. So that happens halfway between the two break-even points. So let me put a label on this so that I don't mess up. This is units, and so then the profit associated with that would be what we get when we plug 50 in. When you evaluate this in a calculator, you should just get 100. So $100. It's a little bit anticlimactic because you were hoping to have a number of like 6 million, but no, we only have 100. Final question here, what price will maximize the profit? So we've been talking about maximum profit. We've answered 2 questions about it. So we have the profit function, we figured out how many units we need to maximize profit, and then we figured out what the maximum profit is. So we are now asked about the price function. Now you might be scratching your head and asking yourself, have we ever even seen a price function? If you look back in the example, the price function was just listed like as an equation in the statement of the problem. So if we grab that from the other page, what we have is that we know price is 1300 minus 1/16 x. If we are talking about the price to maximize profit, that would be the price when we produce the number of units required to maximize profit. In the textbook, they make your profit a capital P and your price a lowercase p. I feel like my notation with my handwriting is not super great, so I'm just going to write price out in words so that it's clear when I'm talking about price. So the price of producing 50 units would be 1,300 minus 1/16 times 50. We'll go ahead and put that in a calculator, and I get 1,296.875. I'm going to round that up to 88. And this would be dollars per unit. All right, we have one last topic to cover in this video, and that is market equilibrium. So recall that market equilibrium is going to occur anytime you have the demand equal to the supply. So we can look at this example. We have a demand function. It's given to us by this. We also have a supply function. It's given to us here. And we would like to find the market equilibrium. So essentially, we need to find the intersection of these 2 equations. Another way of saying that is we need to find the solution to this system of equations. Now, we don't get too much into the details of different methods of finding a solution to a system of equations. I'm pretty much always going to recommend the substitution method because the examples we look at, it's always going to be an efficient one based on the problems I've chosen. Now, it's worth thinking about where to start before we begin the problem. When you use substitution, you have to solve for one of the 4 variables that you've been given. So you might ask yourself, is it easiest to solve for P, Q, P, or Q? The idea here being you just want to get it by itself. And as you scan both of the equations, I hope what jumps out to you is that this Q is not being multiplied by anything, so if you add it to the right side of the equation, which is currently empty, we would very quickly get Q by itself, and that's where I'm going to begin. 2P minus Q minus 38 is equal to 0. I'm going to add Q to both sides of the equation. That gives me 2P minus 38 is equal to Q. And then this becomes something that I can now substitute in to the other equation. So the other equation said P times Q plus 4 is equal to 400, and we now want to simplify. Now there's a couple things you can do here. You might notice you have 2 like terms. You're allowed to add those together. You're allowed to distribute the P in kind of whatever order you want to do. I'll distribute P first, so I get 2P squared minus 38P plus 4P is equal to 400. Now I'm going to combine my like terms. 2P squared minus 34P is equal to 400. And then I will subtract 400 so that I can get 0 on one side of my equation. So I'm going to subtract it, so minus 400 is equal to 0. Okay, we want to solve this, so you have 2 methods of solving a quadratic. You can factor or you can use the quadratic formula. It's your preference. In either case, I think it will be helpful if you simplify first. You're allowed to divide everything by any number you want, but let's divide by something that everything is divisible by. So we get P squared minus 17P minus 200 is equal to 0. At this point, If you do want to factor, you want to find two numbers that multiply to be negative 200. So we could do 1 times 200, 2 times 100, 3 won't work, 4 times 50, 6 will not work, 7, 8. 8 turns out to give us 8 times 25, which is the numbers we want. So right now, if you want to multiply to get a negative number, one of your two numbers would have to be negative. Let's make the 25 negative. And then now when we combine them, a positive 8 with a negative 25 does give us the number in the middle. All right, we can now factor this. P plus 8 and P minus 25 is equal to 0. If you set these factors equal to 0 independently, you get P is equal to negative 8 or positive 25. And then you pause and you consider that this means that the letter P represents a price. So your price could be negative $8 or it could be $25 at your market equilibrium. Okay, but price is not allowed to be negative, so then we will remove that potential solution. So we have half of our answer. We know that P is equal to 25. At this point, we just need to figure out what Q is equal to. So what we would like to do is we would like to plug 25 back into one of our equations to figure out what the quantity is. You're allowed technically to plug it into any equation, so maybe this equation, which would be kind of difficult. This equation is a little bit easier, but this equation, which we have already modified, would be the fastest method. So let's go ahead and do that. Q is equal to 2P minus 38. So then that's 50 minus 38, which ends up being 12. So we have Q is equal to 12. Now, in the context of the problem, Q is a quantity in thousands. Because they wrote it out in words, I am also going to write it out in words. So it's Q is equal to 12,000. But this is our market equilibrium. We have a price and a quantity together. All right, that finishes up this section of notes.